Hello, my name is Keshwani. There's Keshwani, Keshwani. We are here because we want to prepare for GRE. We have been solving GRE math problems out of this book here, the official guide to the revised GRE, the second edition. If you do not own this book already, purchase one immediately. You're going to need it. The problems that we are about to solve are the ones that you will find on page number 154. Please turn to it. Page 154, and today is our lesson number 275. Two problems that you see there on page 154, number 13 and 14, are the exact same problems on the exact same page numbers that appeared in the first edition of the revised GRE. Since we have already done all the problems in the first edition, I'm just going to redo them at a quicker pace. If you need to look at them in more detail at a slower pace, you can always go back and watch the original video. This particular problem that we're about to do, number 13, was something that we did on day number 49, and you will find it there, the same problem being done, as I said, at a little bit of a slower pace. So here's the question. The question is very straightforward, number 13. We are told that two sides of a triangle are 5 and 9, and the question simply is, what could be the third side? That's all they're asking. That's all there is. We are told that we have a triangle whose two sides are 5 and 9. The question is, what could be the third side among the choices that are given to us? This question deals with the most fundamental question in geometry, the most fundamental concept in geometry. And that concept is this. Here's the thing. You might think that that is silly, but this is the question that is being posed here indirectly, implicitly. The most fundamental concept that this question deals with in geometry is, what is a triangle? If somebody were to come up to you and ask you, what's a triangle? Will you be able to articulate that to that person in plain English language, without using any jargon from math, without using any terminology, any jargon from geometry, in plain English language, what exactly is a triangle? What does it represent conceptually? To which the answer is, a triangle is nothing but a detour between 2 points. A triangle is nothing but a detour. For example, I have a choice. I can drive directly from town A. I can drive directly from town A to town B, or I can make a detour like this, or I can make a detour like this. All of these are going to form triangles. Or I can make a detour like that, or I can make a detour like this. These are all detours. Or I can make a detour like that. All of these form triangle, which simply represents a detour from A to B. Instead of driving directly from A to B in a straight line, which is the most direct route, the shortest distance between any 2 points is a straight line, obviously, and anything other than that, of course, by definition, is going to be longer, by definition, because the shortest distance between any 2 points is a straight line. Therefore, it doesn't matter which kind of detour you take. It doesn't matter which kind of detour you make. The distance from A to C, and then from C to B, the distance from A to C, and then B, and then from C to B is going to be greater than the direct route, which is the direct route here. This is the direct route. This A to C and B to C is what we're calling the detour. It says the distance from A to C and then from C to B is always going to be more than the direct route. Now it doesn't matter what kind of detour we are taking. Now how do you say that in the language of mathematics? when we say it doesn't matter what kind of detour it is. In the language of mathematics, we will say that it doesn't matter what kind of triangle it is. It doesn't have to be any particular kind of triangle. In any triangle, whether it's a right angle triangle or an isosceles triangle or an equilateral triangle or an obtuse triangle or an acute triangle, or for that matter an ugly triangle, it doesn't matter. It doesn't matter what kind of triangle it is, hence the use of the article a. It says two sides of a triangle. It does not need to be any particular kind of triangle. And the question is, what is a triangle? Any triangle, any kind of triangle. That's all it is. That's all that we're looking for. Now the question that boils down to is, how do we say this thing in the language of mathematics, in the language of geometry? How do we articulate this concept in the language of geometry? The mathematicians would state the same concept in this manner. I need the room. They would say like this. They would say the sum of two sides, or to be more precise, the sum of any two sides of a triangle, again any triangle, any old triangle, sum of two sides of a triangle is always more than the third side. That is the nature of the thing. That is how nature created a triangle. The sum of two sides of any triangle will always be greater than the third side, because the third side represents the direct distance, the direct route from one point to the other point. And the sum of the other two sides represents the detour. Now let's do the problem. Enough of the talk. We are given two sides of the triangle. We are given two sides of a triangle. 5 and 9. The question is, could the third side be 3? Could the third side be 3? Is it possible to have a triangle where we have three sides, 3, 5 and 9? To which the answer is no, this is not possible. This is an impossibility. This is not possible. Why? Because it says here sum of which two sides? Sum of any two sides in any triangle has to be more than the third side. So if you were to take these two sides here, 3 and 5, the sum of these two sides has to be greater than the third side, which of course it is not. Here the sum of the two sides is not greater than the third side, therefore this is not possible. A is not possible. Let's take a look at B. B says 5. Is 5 possible? I'm going to erase this part here so we can do the B on the top. Is 5 possible? Is 5 possible? The answer is yes, this is possible. This is quite possible, because triangle that you will get is an isosceles triangle. You will have 5, 5 and 9 like this. 5, 5 and 9. 5, 5 and 9. And you can see here, 5 plus 9 is greater than 5, which is the third side. Or 5 plus 5, is greater than 9. See, if you add up these two sides, it's more than 9. If you add up these two sides, it's more than the third side. That is possible. It will make an isosceles triangle. Let's look at C. C says 8. Is 8 possible? 8 in fact is possible. 8 is possible. And how do we find out? Well, just take the different combination and see if it works. We have three sides now. We have 5, 8 and 9. Take the sum of any two sides and it has to be more than the third side. 5 plus 8 is indeed more than 9. 5 plus 9 is indeed more than 8. And 8 plus 9 is indeed more than 5. So this triangle is possible. This triangle is a reality. Do you understand? Let's look at the last one, D. I think I'm going too much of a leisurely pace here. D. In D we have 15. Is 15 possible? The answer is not. 15 is not possible. It is not possible for the third side to be 15 if the other two sides of the triangles are 5 and 9. And I'm not going to write all of this on the blackboard. I'm just going to say it one more time. I'm just going to say it one more time. It says it is not possible. It is not possible for the third side of a triangle to be 15 if the other two sides, we are told, are 5 and 9 for one very simple reason. As you can clearly see, 5 plus 9 has to be more than 15, which it's not. It is not possible. What you're telling me is here's what you're telling me. If this were possible, one speaks hypothetically, if this were possible, what you're telling me is that if I were to drive directly from A to B, I'll end up driving 15 miles. But if I take a detour, and I stop at C, I will drive 5 miles from A to C and 9 miles from C to B. This is insanity. If I make a detour, I will drive 14 miles. But if I take a direct route, I will drive 15 miles. It is not logical. Do you understand? That's it. We're done with this question. Let's move on. Enough of the talk now. Let's move on to the next one. The next question is actually a fairly straightforward question. We are given points that are located in a number line. Here is our 0, here is our x, here is our y, and here is our z. And the question simply is, which of the statements that are given to us are true? Which statements are true? Which statements are true? Let's look at statement A. The statement A says that the product of these three quantities, x times y times z, is less than 0. Well, let's see if that's true. X we can clearly see is to the left of 0. X is to the left of 0, which means x, whatever the hell it is negative. Similarly, y and z, we can see clearly there that they are to the right of 0. If they are to the right of 0, y and z are positive quantities. Y is a positive quantity, z is a positive quantity, x is a negative quantity. So here we have a positive quantity and a positive quantity. Positive times positive is going to be positive, and then product of these two is going to be positive quantity, and positive times a negative is going to be a negative. These two products are going to be positive, and then we bring this down, positive, negative times positive is going to give us negative. So the product of all of these three is going to be a negative quantity, therefore it is less than 0. The statement A works. Now, if you didn't want to do this, if you don't like what I just did, if you didn't want to do it in theoretically that is, if you didn't want to do it in an abstract manner, you could actually plug in some numbers here to make it a little bit more concrete so that it's easy to see. We could have done that too. We could have easily plugged in numbers here. And you will arrive at the same conclusion here. So for example, if x is negative 1 and y is positive 1 and z is positive 2, then we'll have negative 1 times a positive 1 times a positive 2. And we'll arrive, of course, at the same conclusion. That will give you positive 2. Positive 2 times negative 1 is negative 2. And negative 2, of course, is less than 0. Statement A works. Let's look at B. Statement B says x plus z equals y. Well, let's find out, shall we? We have the numbers right there. Our x is negative 1 plus z, which is positive 2. Negative 1 and a positive 2 is negative 1, which is exactly which is a positive 1. Negative 1 and a positive 2 is a positive 1, and positive 1 equals positive 1. It seems to me that it is true. But what if z, instead of being positive 2, what if z turns out to be positive 20? If z turns out to be positive 20, then we'll have positive 19 here. And positive 19 does not equal positive 1. So it is not true. Statement B is not something that is necessarily true. It is at times like this that you need to slow down, you need to take your time, and you must pay the attention. When I was doing this problem, I got it wrong. I blew it. because I was too cocky and I was careless. That's what I did here. This work that we did here is absolutely wrong. What did we miss here? What we missed here is that we are told clearly, the problem clearly states, I'm going to read it to you, it says, on the number line shown above, tick marks are equally spaced. We are told here that x, y, and z are equally spaced. What does it mean, equally spaced? Well, equally spaced means that if you're going to make z positive 20, then y would have to be positive 10, and this guy would have to be negative 10. If that were the case, then what we would have had is x plus y equals to z. Let's see, x is negative 10, y is positive. No, this should be something else here. It's not x plus y, is it? X plus z equals y. X plus z equals y. Y is negative 10, z is positive 20, and that does equal positive 10. Second statement, statement B is in fact correct. It's correct because they are equally spaced. We cannot just plug in any number for z willy-nilly. If you were to change one of these three values, the other two need to be changed as well, because they are equally spaced. The tick mark, as they say, are equally spaced. So statement 2 is also correct. Let's move on to C. C says z times y minus x is greater than 0. Well, let's see if we can do that. Now we can do this in theory, or we can do it algebraically in an abstract manner, or you can do it by plugging in numbers. If you do it in an abstract manner, algebraically, that is, you realize that z is positive. Y is a positive quantity. Okay, listen carefully. Positive minus x, which is a negative quantity. What happens? Positive minus a negative quantity. Positive minus a negative quantity. Negative and negative will become positive. So this quantity will eventually become positive, and this is positive. And positive times positive, of course, is greater than 0. It works. Again, if you didn't like what we just did, if you don't want to do it in an abstract manner, if you feel comfortable dealing with numbers, you can plug in numbers. Let's do it. Let's plug in numbers and redo it. Here's our C, and we're going to plug in the same numbers here that we see, but instead of doing 10 and 20, let's do 1 and 2. Keeps our math simple. So here we have z times y minus x, and our z here is positive 2 times y, which is positive 1, minus a negative 1. You see, the exact same thing is going on here. This negative and negative will become positive, and here we will get positive 2 times a positive 2. Of course, it's more than 0. Statement C works. That's all. Very good. Now, as far as the problem is concerned in the book, we are done. But today is your lucky day. Yes, I know. Today is a lucky day. I know. It's difficult to contain the excitement. So I'm going to give you a bonus problem. What I want you to do is tell me whether or not this statement is true. In statement D, we are making a claim. This is a bonus. This is not in the book. Is this true? X minus y equals 0. X minus y equals 0. Now when people in their haste, you can see what you can do. People in their haste might end up saying that this is in fact true, because what they are looking at is that x is on the left hand side, y is on the right hand side, so they figure, well, if you add them, you should get 0. Oh, you said that 1 minus the other would be 0. Let's see if it's true or not. X is negative 1, y is positive 1, a negative 1 minus positive 1 will give you negative 2, and that is not equal to 0. This statement is not true. Let's do one more on the bonus problem. E, how about x plus y? Is that true? X plus y is equal to 0. X plus y would be 0. X minus y will not be 0. X plus y, as you can clearly see, negative 1 plus a positive 1 does equal 0. So that's true. X plus y does equal 0. X minus y does not equal 0. X minus y do not cancel each other out. The reason they do not cancel it out is because 1 is a negative quantity, so minus a negative quantity actually makes it a positive one. That's it, we're done with this one. We'll continue tomorrow to the third set number 3 on page 155, which is where we're going to encounter hard problems. And trust me, when the GRE people tell you that it's a hard problem, they mean it. You understand? We'll do this tomorrow. We'll start these problems tomorrow. Okay? Bye now.